Good day, everyone. Welcome to Direct Stars. Our subject for today is physics, while our topic is radioactive decay and half-life. Aim of today's lesson is for you to understand the concept of radioactive decay and half-life. Objective is for you to know what is meant by activity and decay, what is meant by count rate from a radioactive source, and what is meant by half-life of a radioactive source. Let's move into the content. Every atom of an element always has the same number of proton, which we call the atomic number, in its own nucleus, but different number of neutron, and that is where we come with isotope. So it is this nucleus that do decay in an element. So an atom of a specific element with a certain number of neutron is called an isotope of that element. So that is where we have activity. Activity of a radioactive source is the number of unstable atoms in the source that decay per second. I want you to know that decay per second. So the unit of activity is called becquerel. So which means 1 decay per second. 1 decay per second. So as the nucleus of this unstable atom, which is the parent atom, decays, the number of that parent atom will decrease, while the isotope decays too, the number of the nuclei in that isotope will also remain decrease. So with this consequence, the activity of that isotope will decrease over time. So when this decreases over time, so the average of this decrease is what we call half-life. That is, the count rate is the number of counts per second. I want you to understand that. So this can be shown on a graph of activity against the time of decaying source. So from here, now when this nuclei decay from this till it gets to this background radiation, so that's it decay per seconds, it decay over time. So we have this till it gets to the final stage of the activity itself. So we'll go with that. Example, a source of radiation has an activity of 2000 becquerel. How many unstable atoms decay in 2 minutes? What does that mean? We need to understand that the count rate, the activity itself, or the becquerel is decay per second. That is, we need to solve it in seconds. So the first thing we need to do here is 2 minutes. We need to change it to seconds. That is 60 seconds make 1 minute. So that is 2 times 60, which is 120 seconds. So what do we do with that? We multiply this with the activity itself, which is the becquerel. So that is 2000 multiplied by the minute itself, which is measured in seconds. So 2000 times 120, and that will give us 240,000. So that means 240,000 unstable nuclei has decayed in 2 minutes. That is the answer for that. So we go with half-life. What do we mean by half-life? It's just from its own word, which is half-life. It's the average time taken for the count rate to fall by half. That is what half-life is. For this count rate to fall by half, that is from 100 to fall by half, that is divided by 2, which is 50. And 50 to fall by half is 25. And 25 to fall by half is 12.5. And so on. That is what half-life is. It's just the average time for the count rate to fall by half. And this is always the same in decay. It is always the same. Okay, the time rate is always the same. For 100 to fall by half is still the same for 50 to fall by half. That is what we call half-life. So from there, we cannot say in general that we can say the initial count rate. That means this is the initial count rate, and let's use n to represent that. Divided by 2. We always divide by 2. The answer will also be divided by 2. So we can use 2 raised to the power of n. And n, this small n, will be the nth term. The nth term means how many times does it decay? That is, how many times does it get to its own half-life? Is it 3rd times, the 4th times, the 5th? That is n. So n, which is the initial count rate, that's the nuclei, the number of the nuclei divided by 2 raised to the power of n, while this small n, small letter n, is the nth terms for it to decay. Let's solve this example here. A particular radioactive isotope has a half-life of 6 hours. That is, 6 hours is its own half-life. Okay? A sample of this isotope contains 60,000 radioactive nuclei. We have capital N to be 60,000. So calculate the number of radioactive nuclei of this isotope remaining after 24 hours. What does that mean? It means 6 hours. That is its own half-life. But we have to calculate it after 24 hours. So we need to understand that 6 hours, 6 hours in 24 hours. How many times can we have 6 hours in 24 hours? We can have it in 4 times. That's 24 divided by 6, which is 4. That would be the small n there. So that's the 4th time that it will get to its own half-life. So we'll go back to the formula n divided by 2 raised to the power of small n. What is n? N is 60,000 divided by 2 raised to the power of n, which is 4. So we have it to be 60,000 divided by 2 raised to the power of 4, which is 16. And 2 raised to the power of 4 is 2 times 2 times 2 times 2, not 2 times 4. That is 60,000 divided by 16, and that will give us 3,750. So I want you to understand that at 24 hours, the radioactive isotope left will be 3,750. So this is how we solve for half-life. So that will be the end of today's class, and thank you for watching. Don't forget to click on the subscribe button and like this video to have more of it. Bye.